Good morning, all of you. We were dealing with abnormal molar mass. On dissolution of a solute, an electrolyte solute if the solute is an electrolyte, for example NaCl or KCl, when it is dissolved, each molecule gets dissociated or ionized. For NaCl, if it is NaCl, Na plus and Cl minus. So there we saw dissociation. Now we will see association, then partial dissociation, partial association. First we saw only one thing, that is dissociation. NaCl, when put in water, dissociates into two parts, Na plus and Cl minus. Then we will be seeing association, means two molecules together make a single thing and it behaves as a single particle. For example, acetic acid in benzene. Acetic acid in benzene. Acetic acid in benzene associates, complete association. Suppose 50 molecules of acetic acid is put in benzene. 50 molecules of acetic acid is dissolved in benzene. We will count only 25 particles because two molecules of acetic acid join together to form a single particle through hydrogen bonding. Two molecules of acetic acid join together to form or to behave as a single particle. So 50 we are putting, but the number of particles we can count only 25. This is complete association. Then partial dissociation. For example, when acetic acid is put in water, you are putting 50 molecules of acetic acid. Only 10 are dissociated. We are putting 50 molecules of acetic acid, but from that 50, in that 50, only 10 are getting dissociated or ionized. So this 10 will become 20 and 40 remaining, 10 got dissociated or ionized. So 10 will make 20. 40 remaining. So 40 plus 20, that is the total number of particles after dissociation, after this partial dissociation. Then comes partial association. Partial association. For example, benzoic acid in benzene. Benzoic acid in benzene. Suppose we are putting 50 molecules of benzoic acid in benzene and 10 are undergoing association. Partial association means all the 50 are not undergoing association. Only 10 are undergoing association. So these 10 molecules will make 5. 10 becomes 5. Now 40 remaining. So 40 plus 5, that is 45 particles in the solution. 45 particles as the solute in the solution. Now we will be talking in terms of moles. Let's see how it goes. That day we saw complete dissociation. NaCl in water undergoes complete dissociation, that is Na plus and Cl minus. Suppose they say it's not complete dissociation, then you have to go for this partial dissociation. In the case of NaCl also, in some questions they say partial dissociation. That time you have to come to this partial dissociation. I said 50 molecules of NaCl we have put. Double the particles will be formed. One molecule of NaCl, one molecule of NaCl gives two particles. This is one particle. Here, two particles. So 50 particles we put. We are having how many? 100. This is 50 particles. Just count the particles. So this is 100. Suppose you are putting 1 mole. So here 1 mole, here 1 mole. Total 2 moles of particles. Now Van't Hoff's factor, which is denoted by I is equal to the total number of moles after dissociation, that is 2 moles divided by 1 mole. 100 upon 50 or 2 moles upon 1 mole, that is 2. Van't Hoff's factor is 2. With this 2 we were putting in that equation, that is delta TB is equal to I kf dot m, I kf dot m, or delta tf is equal to ikb. Delta tf is equal to ikf dot m. Pi v is equal to inbrt, or vapor pressure. In terms of vapor pressure, P naught A minus PA upon P naught A, P naught A minus PA upon P naught A is equal to IXB. IXB. So in all those 4 equations, you have to put that I if there is any type of this dissociation, association, partial dissociation, partial association. Now, let's move to complete dissociation, complete association, complete association. For example, acetic acid put in benzene, CH3 COOH. In benzene, C6H6. So CH3 COOOH. From that side, CH3 COH. Here double bond O. So there is hydrogen bonds between these two. Hydrogen bonding. Hydrogen bonding. So it will act as So this will act as a single molecule. This will act as a single molecule. Suppose you are taking 1 mole here, 1 mole. So you will be having half mole here. If you take 50 molecules here on the left hand side, if you are taking 50 molecules here, you will get only 25 particles there. If you are taking 1 mole on the left hand side and put in benzene, benzene is an organic solvent. So in this case, half mole particles will be there after complete association. So what is I? I is equal to I is equal to total number of moles after association. Now all gone that side. Here nothing is there. All gone that side because complete association, all the molecules underwent association. So what was in the beginning? 1 mole. Now it is half mole. So after divided by before. So I is equal to that half divided by 1, that is half. Total number of moles after association or dissociation divided by total number of moles before association or dissociation. So in the first case we learned what? Complete dissociation. Now it is complete association. Total number of moles after dissociation divided by total number of moles before dissociation, that is this one. Now here total number of moles after association, this is half divided by 1. So I is equal to half. If you are taking 2 here, then it will be 1 here. So 1 divided by 2, again half only. If you are taking 50 here, then here it is 25. 25 divided by 50, that is half. Again, I you can put in the case of that lowering of vapor pressure, elevation boiling point, depression in freezing point, and the osmotic pressure. Now, partial dissociation. Partial dissociation. For example, acetic acid in water, CH3COOH in water. Typical example is acetic acid in water. Water has got high dielectric constant, means it can dissociate this CH3COOH into what all things? CH3COO minus plus H plus. We know that acetic acid is a weak acid, means less number of H plus ions will be produced. That is what is meant by weak acid. So here, all molecules what we have taken, suppose I told you 50 molecules, 50 molecules, 50 particles, 50 particles we have taken, and from this partially only little bit of acetic acid is getting dissociated. For example, 10 got dissociated. 1 if it gets dissociated, then 1 CH3COO minus and 1 H plus will be formed. When 1 dissociates, 1 CH3COO minus and 1 H plus will be formed. Here I am taking 50. From that, partially it gets dissociated, means only 10 are getting dissociated. When 10 gets dissociated, now 40 will be remaining here. 40 will be remaining here. Then here 10 acetate ion and 10 H plus ion, because 10 got dissociated. When 1 gets dissociated, look at that equation. Look at that equation. When 1 gets dissociated, see, look at this equation. When 1 gets dissociated, 1 CH3COO minus and 1 H plus are formed. If 10 gets dissociated, 10 CH3CO minus and 10 H plus will be formed. We have taken how many? 50. 50 particles we have taken, but partial, since it is partial, we say only 10. For example, we say only 10. So here 10 will be there, 10 will be there. So here not 50, now here it is 40. What is the total number of particles after dissociation? That is 40 plus 10 plus 10. That is 60. So Van Hoff's factor I is equal to 60 divided by what was before. What was before? Be- Total number of particles before, that is 50. Before it was 50, 50 solute particles. Now it is 60. So I is this much. Now in chemistry we'll be dealing with moles. Suppose I have put 1 mole. You can take in any way, no problem. 1 mole. From that, how much got dissociated? How many CH3COOH got dissociated? Last year we learned that is alpha. From 1 mole, how many are getting dissociated? That quantity is known as alpha. So alpha got dissociated means how many CH3COO minus? Alpha, and here also alpha. So here, what is remaining here? CH3COOH undissociated, that is 1 minus alpha. So alpha, alpha. So what is the total number of moles? What is the total number of moles? That is, total number of moles is equal to 1, 1, 1 minus alpha plus alpha, that is of CH3COO minus, plus alpha, whole divided by how many in the beginning before this dissociation? That is 1 before putting into this water. So I is equal to, so minus alpha plus alpha got cancelled. So that is I is equal to 1 plus alpha. 1 plus alpha. So this I you will be substituting in those 4 equations. So I can be obtained by this equation, total number of moles after association or dissociation divided by total number of moles before association or dissociation. Next, partial association. Partial association. Now, in this partial association, for example, typical example is benzoic acid in organic solvent. Yeah, benzoic acid in benzene, that is C6H6. C6H5 COOH. This is benzoic acid. When put in benzene, that is C6H6, or you can take it as an organic solvent. Now, what happens? Not all are undergoing association, only partially it is undergoing association. So, partially it is undergoing association. I'm showing it like this: C6H5 COOH from that side, C6H5 COOH. Now, here I show hydrogen bonding. But all are not undergoing. Suppose I am taking 50, as in the previous case, if I am taking 50, and suppose 10 are undergoing association. 10 are undergoing association means here only 5 and here it is 40. 10 are undergoing. So what is remaining here? 40. And this 10 become 5 because it will be acting as a single particle. It will be acting as a single particle. So total is 45. Before is 50. So I is equal to total. Total after association, that is 45. 40 remaining, 5 newly formed, and before it was 50. So this is Van Hoff's factor. Now we are moving in terms of moles. 1 mole. Before I have taken 1 mole, from that alpha got dissociated. Alpha got dissociated from 1 mole. 1 mole means 6.022 into 10 to the power 23. From that, how many got dissociated? Alpha got dissociated. So alpha got dissociated means only half will be the new ones, that is alpha by 2. What is remaining here? 1 minus alpha. So now remaining is 1 minus alpha. What is the total? What is the total? Total is now 1 minus alpha plus alpha by 2. So I is equal to this divided by 1 mole in the beginning. So I is equal to 1 minus alpha by 2. So this is for partial association. Now suppose come back to partial dissociation. In the case of partial dissociation, suppose here 2 are there, then total number here it will be 3. So here 2 alpha plus alpha. According to the situation, you have to calculate. Suppose here K2SO4, K2SO4, K2SO4 when put in water, it undergoes complete dissociation. Complete dissociation. So the total number of moles after dissociation will be 3. See, if it is K2SO4, K2SO4, 2K plus and SO4 2 minus. So here complete dissociation. In the beginning it was 1, now here it is 0, there it is 3. So 3 upon 1 after divided by before. So Van Hoff's factor is equal to 3. Similarly, according to the equation, you have to modify these I values. You have to calculate and modify these I values. You can find out this alpha also. In the first case, I is equal to, if it is NaCl, I is equal to 2 for complete association. In the case of K2SO4, I is equal to 3. So depends upon that equation how it is getting dissociated. Now in the case of partial association, I is equal to half. I is equal to half when it is undergoing complete dimerization, means dimer is getting formed. For complete association, dimer, that product formed is a dimer using that hydrogen bonding. Instead of a dimer, if trimer is formed, if trimer means three molecules are getting connected together. Three molecules are getting connected together. So, what will be the Van Hoff factor? Van Hoff factor I will be, that is 1 by this 3. If 1 mole is taken, how many will be there afterwards? That is 1 by 3. So there the Van Hoff factor will be 1 by 3 upon 1, that is I is equal to 1 by 3. Suppose it undergoes tetramerization. If it undergoes tetramerization, tetramer, what is the Van Hoff factor? What is the Van Hoff factor? What is the Van Hoff factor for a compound which undergo tetramerization in an organic solvent? So it will be 1 by 4. Trimerization 1 by 3. Tetramerization 1 by 4. 1 by 4 divided by 1. Now in this case, that is partial dissociation. Partial dissociation. Partial dissociation. I is equal to, in the case of that acetic acid in water, I is equal to 1 plus alpha, or alpha I is equal to 1 plus alpha in the case of acetic acid when dissolved in water for partial dissociation. What is alpha here? Alpha is equal to, see, 1 will be coming here. Alpha is equal to I minus 1. Alpha is, this is 1 plus alpha. I is equal to 1 plus alpha. So I minus 1. Or if the substance, if the solute is getting dissociated into different, for example, twice x plus y means not only 1 here, maybe 2 or 3. So the number of particles, total number of particles here, how many? Total number of particles here, how many? Using that, you can find out that alpha, that is alpha is equal to I minus 1 divided by n minus 1. I minus 1 divided by n minus 1. In the case of acetic acid, here it is 1. CH3COO minus and H plus. That means total number of particles 2 that time. Like this, total number of 2 particles, total number of particles 2 that time. So here you will substitute 2. Here you will be substituting 2. So I is equal to 1 plus alpha in the case of acetic acid dissolved in water. So alpha you can calculate from here. Alpha is equal to I minus 1. Or if more number of particles are obtained here, if more number of particles, you count the total number of particles obtained here. So that number of particles you will be substituting here n. So in the case of acetic acid, how many? 2. So I'll be substituting 2 here. 2 minus 1, so that is 1. So alpha is equal to I minus 1. Alpha is equal to I minus 1. See the same thing, I minus 1 here, because 2 minus 1 is 1. Now, in the case of partial association, that is that side, I is equal to 1 minus alpha by 2. In the case of benzoic acid, in benzene, that was the typical example we took that side in partial association. Suppose if it is undergoing trimerization or tetramerization, then we'll be using another equation, that is, here what is alpha? That is alpha by 2. Here I is equal to 1 minus alpha by 2, and alpha generally you can write as I minus 1 divided by 1 minus n minus 1. If it is trimerization, n is equal to 3. If it is dimerization, n is equal to 2. If it is tetramerization, this n is equal to 4. N is equal to 4. In the case of dimerization, then this n is equal to 2. N is equal to 2. So you substitute here in the case of that benzoic acid in that organic solvent. So alpha is equal to, suppose if I substitute here, alpha is equal to I minus 1 divided by 1 by 2 1 by 2 minus 1. 1 by 2 minus 1. So you will be reaching from here, you will be reaching I is equal to 1 minus alpha by 2. When you solve this thing, you will be reaching here. So, in the case of partial dissociation, you can use this equation alpha is equal to, here what we found out I, from this you can make alpha is equal to I minus 1 upon n minus 1. I minus 1 upon n minus 1. For partial association, alpha is equal to alpha, you can calculate from this equation. Alpha you can calculate from this equation. Okay, we'll be doing the numericals in the next class. So I value, I is equal to that day, yesterday we saw normal molar mass divided by abnormal molar mass. Abnormal molar mass. In this way you can calculate, or the same I is equal to observed colligative property divided by calculated colligative property. Calculated colligative property. Or I is equal to total moles. We were doing this thing. Total moles after association or dissociation divided by total moles. Total moles before association or dissociation. I can be calculated in this way. Or if it is for alpha, general equation you can use alpha is equal to, this is for I. If you want to write for alpha, that is I minus 1 divided by n minus 1 for dissociation. For association, alpha is equal to I minus 1 divided by 1 by n minus 1. 1 by n minus 1. Okay, thank you.